Recall that tertiary alcohols do not undergo oxidation, and the reason is because they lack an alpha proton. Now you might expect phenol to be unreactive. You might expect that phenol will not undergo oxidation, but the interesting thing is that it actually does, even though it doesn't have an alpha proton. Phenol is readily oxidized than a primary or secondary alcohol. It can be oxidized to benzoquinone. See? It can be oxidized to benzoquinone. And then it can be reduced to hydroquinone, but oxidized back to benzoquinone. Now, quinones are found everywhere in nature, and they exist mostly as ubiquinones, which act to catalyze the conversion of oxygen to water, which is a key step in cellular respiration. Okay. Now, how this is done is that the ubiquinone gets reduced to the hydroquinone, and how it gets reduced is by the help of NADH, which acts as a hydride delivery agent. Now, once the hydroquinone has been formed, then it picks up half a mole of molecular oxygen, right? In which case it's oxidized back to benzoquinone and produces water. So if you add the two reactions together, you see that it catalyzes the conversion of molecular oxygen to water in the presence of NADH. That's something you're going to have to learn when you start looking at biochemistry. Now let's just summarize real quick some of the reactions that we have learned so far. We can recall that if you have a triple bond, you can reduce it to a double bond with any of these catalysts. And once you have a double bond, you can get it back to a triple bond by adding molecular bromine, sodium amide, and water. And once you get to the alkene, you can reduce it completely to the alkene, or you can add molecular bromine and carry out an elimination to get back your alkene. On the other hand, you can take a secondary alcohol and oxidize it to the ketone, and then reduce the ketone back to the secondary alcohol using LAH, or you can oxidize a primary alcohol to a corresponding aldehyde, or reduce the aldehyde back to the primary alcohol. Now you can see these are the different functional groups that are being oxidized and reduced. Here you can see that alkenes are oxidized to the given alkynes, while ketones can be reduced to the corresponding alcohols. Alkyl halides can be reduced to the alkanes, while the alkanes can be oxidized to the alkenes. So there are things that we have looked at. So this is a very nice table or flowchart that will help you to be able to summarize all the reactions that we have looked at so far. Okay, if you have an alkyne, you can get to the alkene by reduction with either Lindlar's catalyst or sodium in dissolving or sodium in ammonia. And once you get to the alkene, you can get to the alkane by reduction with platinum over or hydrogen over platinum. And if you have an alkene, you can always go back to the alkyne using molecular bromine, base, and water. From the alkyne, you can get to the ketone, right? And once you get to the ketone, we can reduce the ketone to the secondary alcohol, or oxidize the secondary alcohol back to the ketone. And then from the alcohol, you can get to the alkene if you decide to use acid, see, you can get to the acid using acid, or you can go from the alkene back to the alcohol using any of this: hydroboration, oxidation, or oxymercuration, demercuration. Once you arrive at the alcohol, you can get to the alkyl halide, the alkyl chloride with tauronite chloride, while the alkyl bromide with phosphorus tribromide. Or you can do an SN2 with sodium hydroxide, or an SN1 with water to go back to your alcohol. So these are different things, these are different strategies that you can implement to go from one to the other. Now look at this example here. You can see that in this first example, you can first reduce it. In the first case, if you use number 1, which is potassium tertiary butoxide, that will give you the alkene. And then if you use number 2 and 3, you will get the primary alcohol. And then from the primary alcohol, you can oxidize it with PCC to the corresponding aldehyde. So you can oxidize it with PCC to the corresponding aldehyde. In this case, you can carry out an SN2, right? And you'll get the corresponding primary alcohol. And then you can oxidize it with potassium dichromate in the presence of sulfuric acid. That will give you the corresponding carboxylic acid. So this is just a quick example of what you can do. Now here, remember we talked about carbon-carbon bond forming reactions with Grignards. If you start out with a ketone and you add an alkyl group to a ketone, you end up with a tertiary alcohol. If you start out with an aldehyde and add a methyl group, you're going to end up with a secondary alcohol. Well, if you add an excess of methyl magnesium bromide to the ester, you end up with a tertiary alcohol in which 2 methyl groups have been incorporated. So these are things you need to remember. Now what if you want to convert an aldehyde to a ketone? To convert an aldehyde to a ketone, you can use a Grignard, right, to put just one R group. Then you can now oxidize. So you have gone from the aldehyde, the secondary alcohol, and you can oxidize it to the back to the ketone. What reagent will you use in this case? You see here, what has happened, a new bond has been created here. Right? A new bond has been created. So the first thing you want to do here is in number 1 and 2. You're going to get the following. You're going to get the secondary alcohol. Okay. You're going to get the secondary alcohol, which can be oxidized with PCC number 3 to get the ketone. See? So these are things that you want to watch for. So that is where we're going to stop today. But you can see that Grignard reagents are very, very helpful when it comes to the formation of carbon-carbon bonds. But remember that once you add a Grignard to either an aldehyde or a ketone and ester, it alters the number of carbons present.